Welcome back. We are on our way. This is module number 4, and we are going to be halfway through the technology modules when we finish this one. LDSH 5803, Technology and Leadership. We're going to be looking at big data. And you might think to yourself, look at that byte. That is a really big byte. That's not what we're talking about. All bytes are the same size. What we're talking about here is huge, copious, large amounts of data. Now, big data refers to data storage as well as data processing and the applications that are made with these large amounts of data. And we have a lot of things to think about when we think about big data. It's not just, oh, there's a lot of data. What does it take to process it? There are storage technologies. There are the kinds of data that we're collecting in addition to just bits and bytes and facts and text. We might have video, we might have imagery, we might have all kinds of unique and interesting data formats in addition to just the large volumes of it. So big data refers to something that is a large, we're talking about terrifically large, galaxy-wide large data sets that are complex because they have a lot of different kinds of elements. They're complex because they cover a number of different um, bits of information from various different sources. And usually, big data involves data that is generated in high volume, velocity, and variety. And that is the three V's. When we think of big data, we want to think about the three V's. We have volume, which is huge data sets, extremely large data sets, terabytes and petabytes of data. And this data comes from, pardon me, a number of different sources, including social media, sensors, transactional data. So you think about social media, you think about the number of people worldwide who are on social media. Let's take Twitter as an example. That is generating a huge amount of data every single day, every hour. Now, what are we going to do with that? And there are different big data applications that are monitoring that, following it. And they're not looking just for small trends, they're looking for big trends throughout all that data. And so this is the volume of it. And then we have the velocity of it. And the velocity refers to, let's say that we have a worldwide set of Internet of Things that are sending data to a central processing location. That data will be coming in a very high rate in terms of bytes per second. It'll be coming in as not just megabytes a second, perhaps gigabytes per second. More than that, we may be getting terabytes per second from all these different sources where we're getting the data. And that velocity of data arrival gives us a number of interesting problems. How do we get it stored? What if we have to process it as it's coming in? How are we going to do that kind of stuff? And finally, the variety of data, and I made reference to this just a minute ago. There are many different formats of data, including structured, semi-structured, unstructured data. Structured data is very much like a traditional database where we have specific columns. You think of a spreadsheet, that's structured. The data is related to each other for ease and quick um, retrieval. Then we have semi-structured data, which is kind of a hybrid between structured and unstructured data. Unstructured data is obviously just raw data that's been dumped into some sort of data storage format for processing. And so all of these can include all the different kinds of things that data can be stored in. They could include just text, images, video, audio. They could be binary data. It could be binary sampling data. I'll give you an example in a little while related to electrical grid information. And big data is usually characterized by special tools that we have to have and techniques that we have to use in order to manage, analyze, and process this data. And there have been a number of tools that have been developed over the years, like Hadoop and Spark and NoSQL databases. And then we have machine learning algorithms in order to process and do something with this data. Hadoop is a popular open source distributed computing framework, and it's designed mainly for storing and processing large data sets. It has two different parts. It has its file system, and then it has its processing engine. The file system is designed for specifically for large data sets, and it works across a cluster of machines. If you're not familiar with the idea of a cluster, you have a number of machines that are working together and tightly organized and built specifically to be able to share loads and move loads and be reliable and resilient to failures. And so this Hadoop system, the file system will run across a cluster of servers. And then it has a MapReduce processing engine, and this is a unique processing engine that's built for parallel processing. That's kind of why we think of it in terms of working on a cluster, because it's a parallel processing framework, and it gives us a platform that can be spread across multiple different servers in order to process the data in a distributed manner. Then you have what we call not only SQL databases. SQL databases are very well known, and they've been around for years. They're still very important to us. But SQL databases try to organize the data into columns that are related. You might, for instance, have one database that has a patient name, a patient ID number, and then that ID number is used as a key into another table that would retrieve patient appointments or patient information, things like that. So it's highly organized, structured, but a not only SQL database is a type of non-relational database that can handle these sort of large and unstructured database. They're not based on the strict data schemas that you would see in a SQL database. Rather, they're designed to be more flexible and scalable to deal with, again, the large amounts of data, but flexible in a way that helps us deal with the fact that we can't just organize this thing into a series of columns that make it easy for us to retrieve and correlate the data that's in there. And finally, we have these large data warehouses. These are very specialized databases, and they are made for large volumes of data. They're made specifically for big data. They're typically used in business applications when someone is looking to go through huge amounts of data and make better decisions. And one of the things that I immediately think of is, for instance, financial data. There is a ton of financial data that's generated from the stock market, that's generated from various different financial feeds every day. And that data, there are a lot of organizations that want to process that data in new and interesting ways in looking at large, huge amounts of data. And that hopefully gives them some insight or advantage into financial trading systems or into what's happening within a particular market. It's maybe the oil market or the grain market or something like that. They're looking for trends that nobody else is going to find, and they hope by looking through huge amounts of data that they can get an advantage that they can take and use for business success. So we talk about not only SQL, the NoSQL. This has a flexibility in its schema. When we talk about schema, we talk about how bits of data relate to other. What is the scheme? What is the relationship that's defined? And traditional relational databases have really well-defined tables. They have keys. They know exactly how the data in column 3 is related to all of the data in 2 other tables, and it's very, very well defined. And there is quite an right by now quite an old and ancient science to that. By old and ancient, I mean old and ancient in the data community, in not data community, in the computer world. Uh, Back in the 1980s, already SQL databases and structured databases had been well researched and were already, a lot of these techniques for structured databases were already in place. We talk about not only SQL, we're talking about something that's a little different, something that's not quite as structured. And so traditional databases, when you would look at that, you would think of it as if it was scaling vertically. If you wanted and needed more resource, you would add a single more resources to a single server, like a better processor or more memory and stuff like that. However, with NoSQL, what we have is horizontal scalability. Instead of adding more to a specific server, we're able to add more storage and processing power by adding more servers into our cluster per se, or adding more RAID systems into our data storage system, into our disk drive systems. And NoSQL also has the advantage that it can work on a ton of different kinds of data types. It could be structured, but it doesn't have to be. And so if you look at some examples of that, you may know JSON, XML. If you are not familiar with those, Google those terms. XML is a very, very, very heavily used way that can organize data and information hierarchically. It's used heavily in a number of different programming languages. Python uses XML quite a bit. When we look at, for instance, configurations of devices in a data center, a lot of times those configurations for how a specific processor in a data center, that configuration is stored in an XML file because it's highly structured. And NoSQL can work with that. But NoSQL also works with things like images and videos, which it takes doesn't take much creative imagination to think, well, obviously those kinds of things are going to generate a ton of different a ton of amount of data. So traditional relational databases are typically limited to structured databases with predefined columns. Not only SQL is able to be much more flexible in the data that it can process and poke through. And the other thing that we get from it is high availability. So these databases, because they're working on a cluster, some node in the cluster fails, they're built to not crash as a result of that. They can move the work that was being done on that node somewhere else, and the data that that node might have had primary access to is accessible in other places. Typically, in fact, what we're actually going to have is we're going to have what's called a storage area network. SAN is what you'll hear that referred to. A storage area network is you've got the processors, and they are no longer attached directly to the hard drive. You look at your laptop that you may be watching this on, you've got a processor in there, you've got a hard drive in there, and they're connected to each other. And if the laptop crashes, then both are unavailable to you anymore. But in a large data center, especially with big data, what you actually have is you have machines with custom processors, local memory, but they don't have the hard drives attached to them. The hard drives are connected via a network, and all of the processors can, through the network, get to all of the data storage devices. And so that gives you a lot of flexibility. If you lose a disk drive in the disk drive storage area network system, you usually have some sort of RAID system, and that disk drive can be, um, you can tolerate its loss. In fact, you can oftentimes rebuild the data that was on it because of the redundancy that you built in the way that SAN and RAID systems work together. So with the high availability of a NoSQL database, what we've got is data that's always available, processing that's always available, and resiliency. If we lose something, we've got that. Another kind of processing that we go through is something called batch processing. And batch processing is an old term. It's been around since the 1970s, maybe even in the 1960s, but certainly in the 1970s, it was already common. And the way we would think of a batch, you think of a batch of something, a batch of products that have come out of a factory, and they're just a group that came together, and they came out as a set, if you will. Well, when we think about batch processing, we think, okay, I've got a bunch of data here, or I have a bunch of jobs to do, and they're not interactive. That's really what we're thinking about here. If they were interactive, you would be sitting at your terminal, or somebody would be sitting at their terminal, or perhaps it would be an automated system that would be going back and forth, querying the data, poking through it. But there'd be someone involved with it. With a batch, you say, okay, this is going to be something that we're going to turn on, and it's going to run for 36 hours, and then the processing will be done, and then we'll see the results. We won't see the results as we go. We'll do a batch of processing, and then we will see the results. And so with big data, because the data sets can be so large, oftentimes we have to do a batch of work on it. And so what we do is, as kind of mentioned here, you might have a bunch of data that's been collected over a while. It's been stored in some sort of data warehouse or cluster, and then we run our jobs against it. And batch processing is really well suited for this kind of work, because you send the job off, and it works for a while. You can do other stuff. Your computers can do other stuff while that job is running in the batch, and then we get data, the data back that we want. The example I gave here, I referred to it earlier. There's a really interesting thing that a lot of people don't know. Did you know that in different parts of the world you have different electrical grids? The main continent of Europe has its own electrical grid. The United Kingdom has its own electrical grid. Japan has its own electrical grid. North America has its own electrical grid. And what a lot of people don't realize is those grids run on a frequency, number of cycles per second, but that frequency varies second to second. The frequency might be running at 59.2 frequencies cycles per second, and then a second later it's running at 59.4. It's not perfect. But one thing that is true is that the entire grid is running at the same speed at the same time. And here's an interesting big data application. Did you know that there are people who record the variance in the frequencies of electrical grids from second to second? And they have huge amounts of data that store the exact frequency and an exact given time of day. What's interesting is if you take like a 10 minutes or 600 seconds, which would be 600 samples, that those 600 samples are unique across, well, fairly unique across all time. So one of the things that recently came out was there was a court case, and in the court case, the police had made some wiretap recordings of the criminals hatching their plans. And then when these were presented in court, the defense lawyers said, hey, the police were dishonest. They patched this together. They actually had recordings from a number of different times, and then they patched it together to make it sound like what you heard was the plans, but really this is all taken out of context. Well, the prosecuting attorney got an expert to look at this, and what he did was he filtered the recordings out because the recordings were made and they were connected to the electrical grid. So he filtered out the voice, but he was left with the background frequency of the electrical grid in the recording. And then he was able to take like 20 minutes of the recording and see how the frequency changed from second to second. Now, here comes the batch job. He took that 1,200 samples, and then he sent it into the big data that was stored of all of the samples over years and years and years. And then this expert was able to show that this recording that I got from the cops was actually made on the day that they claimed it. But also because of the pattern that had been saved in the big data, he was also able to show that no, this wasn't patched together. This matches exactly the pattern in the grid at the time. The police said they recorded it, and therefore the data was good. The police were telling the truth. And of course, the defense lawyer's argument fell apart at that point, and they were able to get a conviction based on that. So here's an interesting application of large data and taking a very small sample, and you need to search through that data to find out when that sample occurred. That's batch processing. And so I think that's kind of an interesting way to think about that. You can think of all kinds of many different applications. All right, and then we have stream processing. Now, this is real-time processing. Let's say that you are a stock trader and your company has all this data coming in at high velocity, all the trades that are happening. And what you want is you want to get an early warning if there's a trend picking up, if something's starting to take off and go up or go down and you need to get out of it. You want to get in that early before it's too late. And so with stream processing, we look at real-time data from all kinds of different sources. Now, it could be from financial networks, it might be from social media. We talked about that earlier, Twitter, other sources, or it could be Internet of Things devices. You could have samples that are monitoring uh, worldwide weather trends or something like that. And this data is coming in all the time, and you're going to process it in real time. There are a number of different frameworks. I don't expect you to become an expert in any of these, but it's important for you to know that there are different approaches and systems that are used to process this data in real time. And when you're looking at real-time data, this is where the velocity of the data, we talked about that in slide 2. How fast is the data arriving? How much data is arriving per second? How hard is it at that rate to process it in real time? What techniques can we use to do that? And so stream processing techniques are used to catch the data in real time so that we can respond in real time. The main advantage of it is that we get that immediate action that we can take maybe before other competitors, or put in a nicer way, if you think that competition can be kind of crass, is maybe we're able to respond to changing earth conditions. Maybe we're able to respond to societal events that are starting to take place, and we can do something to tamp down something that might be really bad for a country or something like that. Now, when we have real-time, high-velocity data, we don't really get a choice on how much resource we have to apply. We have to apply enough resource. One nice thing about a batch job is you can start the process and it will just work and work and work and work. And when it gets through, you get the answer. You might want to get the answer in 24 hours, but it takes 30 hours. But it's a batch job and you kind of live with how long it takes. You really can't do that with real-time data. You have to get the answer as it's coming in. If you fall behind in processing the data because it's coming in too fast, then you're not really processing it in real time anymore. And so this presents a real stress on these systems that try to manage this data. Now, another way that we can do this is we can have what we call distributed processing of large data. And this is similar to the cluster that I mentioned earlier, but we probably a cluster is actually a localized set of processors and memory that work together as a virtual single unit. But with distributed processing of large data, we might actually have work being done all around the world. And you can probably think of some applications of this distributed processing of large data. Maybe some of the Bitcoin mining that goes on could be considered distributed processing of large data. In fact, I tend to think of data communications as a distributed processing load because we have data packets flowing all over the world, millions per, no, billions and trillions per second. But each individual router doesn't have to handle that whole load. Each individual router handles its own piece of it. And so we have a distributed application in which they all cooperate around the world. And so that's kind of what we think of distributed processing. We can process large amounts of data by sharing parts of the load. Another interesting example that is still going on today, I think it was kind of more popular to talk about maybe 20 or 30 years ago, is something called the search for extraterrestrial intelligence. And you may be aware of this. There are some satellites that are gathering electromagnetic information, electromagnetic signals that are coming from deep space. And then, if you want, you can participate in processing that data. You can sign up when you're not using your laptop. Your laptop will go to the SETI site, get some data, process it, send the results back. And the exciting thing for people was, hey, I might be the one who discovers that there are aliens out there somewhere. And this is a distributed processing application because we distribute out the work to process all this data coming in from deep space as a way of trying to find if there's an extraterrestrial signal somewhere in all that noise. And so if we do it right, we can process a ton of data because we have processors from large varied locations and sources that can look at the data together. So one of the things we look at is data ingestion, and you think about ingestion like I'm going to eat something, and this is kind of like, okay, we're going to eat this data. We're going to bring the data in from a number of sources. We're going to put it in a central system, and we're going to ingest it or process it. And the sources of data again could be any one of those things we've already been talking about: IoT, social media, financial transactions, things like that. And here we see Apache Kafka again, and here's a couple other technologies. Kafka is an open source distributed streaming platform. I think that's very interesting that it has taken off so well. It was originally designed for LinkedIn, and it's a publish subscribe messaging model. What that means is there will be publishers, processors that are sending data out. And if you want to know about that data, then you have to let that processor know I'm one of your clients and you are subscribing. And that's very similar to the original use of the word subscribe. I'm going to subscribe to the newspaper. I'm going to subscribe to a magazine. You subscribe to various different Twitter accounts. When you follow them, you say, hey, I want to follow that one. I'm going to subscribe to it. And when they send something out, I get to see it. And that's what this is doing here. It's you don't have hard connections between things. Rather, you have subscribers, which you can kind of think of as, I'm sorry, you have publishers who are originators of data or the results of data processing, and then you have subscribers, people who take the data and maybe do something with it on their own. This allows for uh, someone to have centralized data collection and management, but you can still do some different ways to process the data. Now, it can have a lot of resource drain, and it might introduce some delays or data loss if you don't set it up right. So it's an architecture that has to be built just right. But this is an idea of processing data. And here's same thing. When we talk about data processing, what we're really talking about is getting something out of it, transforming a whole bunch of data that doesn't seem to be related into something that's meaningful, something that we can get an insight out of or get some special knowledge out of. A lot of artificial intelligence, and we will have a section on AI later, a lot of artificial intelligence systems are really just systems that are looking for patterns in data. And when they find it, then they report that. And you can watch, there are a number of videos out there on TED where people have talked about some amazing discoveries that AI systems have made. One of the ones that really struck me the first time I learned about it was they turned AI loose on a number of different medical imaging of different kinds of cancers. And the AI found an interesting correlation that doctors had never noticed. And it turned out that this was that they could spot if this was happening in the medical imagery, in the MRI scan, if the AI saw a particular kind of cell or a particular kind of formation, it almost always led to cancer later on. Well, doctors didn't know about that. They had never noticed that connection before. And so it gave them a new tool to describe and discover cancers well in advance of when they might have been seen before. And so here's an AI system that processed data looking for a unique insight. And in this case, of course, it was one that would save lives. Fantastic kind of stuff. There are a number of technologies that can do that. Hadoop shows up again. It's a processing ecosystem. In other words, it's not just one application, it's a number of things that work together. And we talked about this earlier with the file system and the framework. The framework is used for distributed processing of really huge data sets. So when we have a high amounts of data, and the main advantage of data processing systems that we get is we get more efficient and scalable processing. And scalable is a word that as a technology leader that you're just going to live on. It has been around for as long as I've been working with technology, which is a long time. And when something is scalable, what we mean is as the load increases, maybe even exponentially, or as the amount of data increases, maybe even exponentially, we can keep up with it. We can grow as fast as the demand grows. And that's something we're always looking for in our technology systems, is that they are scalable and growable. Now, there's a disadvantage in that it may require more resources, may require more expertise. You may have to pay more for rare expertise to get this stuff up and running. Finally, we have data storage, and data storage involves putting stuff into some sort of location or format. But what we're really thinking about when we think about storage, we're thinking about, hey, I want to keep this data. Why am I keeping this data? Because I will want to look at it again in the future. I may have a new insight that I'm looking for historically, and so I want to be able to process the same data again, looking maybe for different bits of information later or different insights. There are a lot of technologies that can be used for data storage. Relational databases, we already talked about, they're highly structured. NoSQL databases, not so structured. Data warehouses and data lakes. Now, a data lake is, when you think about a lake, you think about a huge repository of water. That's why we call this a data lake. It's going to be a huge repository, large volumes of structured, semi-structured, and other kinds of non-structured data, and they're all just stored in this quote lake. They're designed to store data in its raw format. And so there's some advantages when you keep data in its raw format. If you've processed data, you may lose something in the processing. But if you have the original raw data and you come up with a new technique to process that, hey, you can go back to the raw data. So a lot of times big data has the problem and challenge of, we have all this original data that was unprocessed. How are we going to store it? And so some solutions like data lakes can do that. Now, your choice is going to depend specifically on the application you have, what kind of way in which you're going to choose to process it, all kinds of things like that. Now we're going to talk. I've said that multiple times, but as we are working through this course, we do find ourselves saying, "Hey, we're going to talk about this more in the later." Well, we will get to it. But big data is one of the big things behind machine learning, and as just even in the last 4 or 5 months, with this is 2023 as I'm recording this, and ChatGPT has really taken the world by storm with its interesting and unique applications and responses that it can make. And so we look at, hey, how can a machine learn? And without getting into the details of it, it is extremely complex. But one of the ways in which machine learning works is we try to mimic the way brains learn by building patterns and building connections over time. And what machine learning tries to do is it tries to make predictions or decisions without being explicitly programmed to do that. What it's programmed to do is look through data and find associations, find links. And so it's a kind of algorithm where the model is trained on specific data sets. One of the things that's really cool about ChatGPT that I am still anxious to see if I can get my hands on is you can take a ChatGPT engine that is untrained and feed it a specific data set, and now you can talk to ChatGPT about that data set because it becomes sort of an intelligent way that will converse with you and give you ideas. And it will even look through the data set and find connections. So there have been some that have been given large textbooks, and then you can query the Chat GPT about that textbook. So it's trained on a specific set of data. And usually the data had a predefined set of outputs or outcomes. And what we try to do in machine learning is have a mapping function from the input data to our outputs, to the results of our processing. And oftentimes the outputs are unexpected. There are also a number of, I've seen a TED talk that shows how sometimes the results are nonsensical. A good example is they fed a information about how a virtual robot would walk, and they asked and then they gave this machine learning system a difficult landscape, but could it build a robot that could reach the end of the landscape? And so it started coming up with some really crazy things like um, a robot that fell down and rolled would do better than one that attempted to walk. Or build a robot that was really tall and just have it fall over and it will touch the end, and therefore it succeeded. So it can come up with some honestly nonsensical solutions because it's not given limits in terms of what we would think of as common sense. We wouldn't build a robot that was a mile high and just have it fall over and reach the destination a mile away. Or we probably wouldn't build a robot that would fall on the ground, stand up, and fall on the ground again. We would want a robot that walked because that's common sense to us. But what the machine learning does is it tries to find other ways to satisfy the requirements that perhaps were unexpected. And this is also a way of thinking about deep learning. And I've already mentioned this before, that it uses artificial neural networks. Deep learning algorithms are very well suited for complex tasks, unstructured data, and they are sometimes used to process big data. All right, the last thing that we have on big data, and this comes up in all of our technologies. One of the things that is really interesting about technology is how technology opens up or enables new ethical questions. Now, I'm very careful about how I think about this. There are a number of ethical questions that are not really new because we have a computer that's processing them. An example is it has always been important for your physician to keep your medical records private. And electronic processing of medical records does not change that, but it does make it possible for people to more quickly and aggressively steal your data or do something with your data. And so what we're dealing with is not so much a new ethical problem, but a new exposure to that ethical problem. So that's one avenue in which technology creates ethical exposure. Then there are some things that are actual ethical problems. I think a great example goes with AI, and I'm sure we'll talk about it more in that module. That is, um, let's say we have, well, some of you may have used the DALL-E AI painter. I've made several paintings with that. And what it does actually is it goes through a vast big data library of paintings from all throughout history, and you can say, hey, paint me this. And then it uses what it's connected together to actually create a new picture that you ask for. You can have it made in certain specific styles. You can do all kinds of stuff. But here's the ethical problem. It has kind of borrowed its patterns from maybe famous painters like Andy Warhol or uh, oh, I'm drawing a blank all of a sudden. The guy who did Starry Starry Night, Van Gogh, other kinds of famous painters. And is it stealing from them? Who gets the credit? If you ask AI to write a computer program for you, and what it did was it went into its knowledge and it borrowed from some other programmer's proprietary or from public source that should have had a license attached to it. What do we do with that? So big data brings up interesting ethical and privacy issues along those lines. Big data enables these because now we can put together data that previously could not have been correlated. And this is an example where technology actually opens an ethical issue. So again, there are kind of two ethical avenues that get opened with technology. One is it's not a new ethical problem, but now it's being more exposed because there's larger amounts of data, like private data, that we have to keep. The other one is it is actually a new ethical problem that we have that was enabled by the way in which our data was put together. And so we have a number of different obligations and responsibilities. We have to maintain people's privacy. That's a big deal. If we're not careful, big data can be biased. It might not be intentionally biased, but it's possible for data to be collected and stored. For instance, you could have data, worldwide weather station data, and you only collected data from city temperature gauges. Well, your data is now biased. It doesn't carry temperature information from rural areas. And so as a result, you may get bad results. It's oftentimes difficult to figure out how the computers, especially with AI and machine learning, came to the conclusions that they came to. And so, one of the things that, for instance, there's some new rules that have been developed in the last 10 years and proposed around AI systems, that AI systems should be what's called transparent. It should be possible for us to explain what were the links and connections that happened that allowed this result to be made so that we can analyze it for common sense and for ethical problems. And so by that, what we're saying is it should be explainable. It should be transparent. We should be able to see into it. Obviously, big data is a rich source of information for nefarious actors. And so we have to make sure that we secure the data. And then sometimes there are questions about who owns and controls the data. Uh, how can it be used? Are the applications people want to use it for ethical? We don't want someone to take data and apply it in a way that allows them to commit a crime, things like that. So technical leaders have to be responsible for this, and they have to set policies in place and raise priorities among the other rest of the organization so that the rest of the organization takes this very seriously. This is a very important thing, and we can't afford to uh, ignore it because we can get ourselves in big trouble if we do. All right, thanks a lot. That was the talk on big data. You have your homework, and it is due. I would have to look it up. It is due in the next thing, and so good luck to you. And please email me if you have any questions.